All right, hello, everybody. Welcome back. Today we are going to finish chapter 3. We're going to talk about asymptotic behavior of rational functions. We're going to put together everything we've learned earlier in the chapter and even some techniques that we learned earlier on in the course. It's all going to come together in a very beautiful way to give us a complete analysis of rational functions and their graphs. Also going to introduce some cool concepts that you may not have heard of before. Let me get the slides up and let's get going. All right. So we're going to start with just some motivation. It's always a good place to start. Global behavior and behavior. We're going to talk about horizontal and slant asymptotes or oblique asymptotes. We're going to recall this important lemma that we've used a few times now, the division lemma for polynomials. Then we're going to review an important interpretation of that lemma. And that's really what's going to help us understand the asymptotic behavior of these rational functions. Then we're going to talk about non-vertical asymptotes. We're just going to generalize the idea of a polynomial asymptote, or I just like to call them non-vertical because you basically have vertical asymptotes and then not vertical asymptotes. So we'll generalize that idea. Then we're going to talk about asymptotic equivalence. This is one version of asymptotic equivalence that shows up a lot in math and science, and that's one of the reasons I wanted to include it here. This is a perfect place to talk about it because once you understand what asymptotic equivalence is in this context, then it makes understanding what's going on with a rational function very clear and easy to understand. Then we're going to finish up by analyzing and graphing a rational function. I've got three really good examples to kind of showcase how that's going to work. And then we'll finish up with some good old helpful technology. Mathematica is going to help us with our analysis. So here we go. In the previous section, we saw how factoring the numerator and denominator of a rational function can give us local information, right? Looking at things like the vertical asymptotes, the zeros, the wholes. That's what factoring does, gives us local information. Now, excluding the wholes, the real zeros of the numerator gave us the x-intercepts, the real zeros of the denominator gave us the vertical asymptotes. So in this section, we're going to use a very familiar algorithm, the division algorithm, to help us determine the single, unique, non-vertical asymptote of a rational function. And we're going to get a really handy corollary that can help us characterize roughly what these things are going to look like. Every rational function has a non-vertical asymptote, the simplest case being a horizontal asymptote, all right? A horizontal asymptote. So let's talk about those for a minute. I've got this function here, f of x equals x squared plus 3 over x squared plus 1. And let's just look at the end behavior by sampling some points, sampling some x values that get larger and larger in both directions. So very close to the origin, f of x is spitting out these numbers, but then as x gets larger, you'll see that the numbers start getting really, really close to the number 1, like 1.11, 1.07, 1.01, 1.0001, 1.000002, and so on. So basically, as x is getting really large, the output values, f of x, are getting really, really close to the number 1. They're converging to the number 1. Let's take a look at the graph. This is what it looks like. Zoom in a little bit. Again, you can see that when x is 0, we got 3. And then this graph actually has some symmetry. It's symmetric about the y-axis, so it's an even function. You could even test the formula itself and you would see that it's going to be an even function. But what I want you to notice is that the graph is kind of shallowing out and leveling out here as it approaches the number 1 on both sides in this case, right? So what's happening here is this dotted red line is a horizontal asymptote of the function. So what is a horizontal asymptote? We need a specific definition, and then I'm going to show you some examples of it to kind of hammer things home. So here's the specific definition. The line y equals L is called a horizontal asymptote of the curve y equals f of x if the limit as x goes to negative infinity of f of x is L, or the limit as x goes to infinity of f of x equals positive infinity of f of x equals L, or both. So in essence, a horizontal asymptote occurs when the end behavior on either end converges to some finite number. This number L could be any real number. It could be 1, it could be 2, it could be pi, it could be negative a million, it could be anything. In the previous example, this one, This one, the end behavior is actually the same in both directions. The limit as x goes to infinity of f of x is 1, and the limit as x goes to negative infinity of f of x is 1. So in this case, they're both converging to the number 1. All right. So let me show you some other graphs of these things. I want to zoom in on a couple of them at least. Here's a kind of a funky looking graph. Oh, wait, let me switch to this. There we go. Here's kind of a funky looking one, right? So more locally, I'll say, or closer to the y-axis, this graph does all sorts of crazy stuff, wiggling, jumping up and down. But you'll notice that as x goes to negative infinity, it's kind of leveling out, and it's going to converge to this line y equals L, whatever the number L is. So there's one example of a horizontal asymptote and what the graph could look like. Here's another one. This one's much more smooth. It's just kind of smoothly going up to the line y equals L. Again, this is the limit as x goes to negative infinity, so we're talking about end behavior in the negative direction. Here's another one, and this kind of illustrates a point that I'm going to really emphasize in the next example here. But this one, this graph kind of goes whoop, whoop, and then it goes this way. Now, you may not be able to see it, but as x continues toward negative infinity, this curve, the blue curve here, will converge to that line y equals L. But one of the things I wanted to point out about this example, and then I'm going to turn it up a notch in the next one, is the fact that the graph crosses this line. All right. So the graph crosses this horizontal asymptote. And that is something that I'll just say is allowed. So graphs of rational functions, they can cross horizontal asymptotes. They can cross slant asymptotes. They can cross any non-vertical asymptote. So that's an important detail I want to mention. If somebody stops you on the street and they're like, "Hey, can a function cross a non-vertical asymptote?" The answer is yes. It absolutely can. It doesn't mean that it will always, but that it can. Contrast that with vertical asymptotes, and vertical asymptotes graphs cannot cross those. They cannot cross those. The reason is, if you remember, crossing a vertical asymptote would mean allowing division by 0. So that's why when you see vertical asymptotes, those are like impenetrable walls. And if you try to penetrate them, everything blows up because you're trying to divide by 0. So, moral of the story here, graphs can cross non-vertical asymptotes. Maybe they even cross them a whole bunch of times, as we're going to see in this example here. So here's a couple other graphs of horizontal asymptotes. Now we're going the other direction. So this first graph here, the limit as x goes to positive infinity is L. And that's this horizontal line here. That is the horizontal asymptote for this graph. You can see it's crossing once over here. That's allowed, right? Here's another example where it's just kind of smoothly swooping down, and that graph will converge to that line as x gets larger and larger. And then here's a really funky one. This one is pretty cool. This one is wiggling back and forth. It's going down, up, down, up, down, up, down, up, down, but this line is still a horizontal asymptote of that graph, okay? So in this case, the graph is actually going to cross the horizontal asymptote infinitely many times. It's going to cross it forever and ever and ever. It's going to keep bouncing up and down, but you'll notice that the oscillation that you see here is damped. The oscillation here is decreasing as x gets larger. So what happens is, quote, at infinity, the graph converges to that horizontal line. So again, these non-vertical asymptotes, they can be crossed even infinitely many times. That's totally allowed. But here's a nice example of a graph crossing it infinitely many times. Okay, so now we have an idea of what horizontal asymptotes are. Let's look at a common example. This is one of those graphs that you should have memorized. This is the graph of 1 over x, right? And the limit as x goes to positive infinity is 0. You can see the graph converges to that line y equals 0. And the limit as x goes to negative infinity is 0 as well. So it swoops up and converges to the line y equals 0. So if even just one of these behaviors occurred, that would mean that y equals 0 is a horizontal asymptote. All right. Okay. Now let's go up a notch. Let's talk about slant asymptotes or oblique asymptotes, their equivalent. So linear asymptotes that are not vertical or not horizontal are called oblique asymptotes or slant asymptotes. So here's an example where the asymptote of this function is y equals x plus 1. And again, you can kind of see you've got this behavior here. And what I'm saying is as x goes to infinity, the graph or this function, f of x, r of x, whatever, is going to converge to this line. That's what's happening there. And it's actually going to happen in both directions. So this is what we call a slant asymptote, all right? A little note here, we're going to see this in one of the examples. We're also going to see it as a part of a corollary that we're going to get in a minute. But slant asymptotes occur when the degree of the numerator of a rational function is exactly one more than the degree of the denominator, all right? So let me see here. Okay. Yes. All right. So, oh wait, let me go back to these slides. There we go. It's a little better. Okay. So now let's just talk about non-vertical asymptotes in general and just the idea of what are called asymptotics. Linear asymptotes exhibit one form of end behavior, but the reality is there are infinitely many asymptotic possibilities for the end behavior of a function. And this is something that I really want you to keep in mind. The way that these functions converge depends a lot on the function itself. So in the case of rational functions, the end behavior is determined by what we call the dominating function. And that dominating function happens to be the quotient that you get when you divide. It's that. Literally, it's that. So in other words, for rational functions, the equation of the non-vertical asymptote itself, you can produce it by just running the polynomial division algorithm. You just do the same division algorithm that we saw a few sections ago, and that will produce the formula, the function that gives you the polynomial asymptote of that rational function. That's the basic idea. All right. So just a quick reminder. Here's this thing again, Euclid's division lemma for polynomials. I won't read the whole thing over again. You can review it on your own if you would like. But the basic idea is if you're given a rational function, you can always write it in this form here, q of x plus r of x over b of x, all right? Where the degree of r is strictly less than the degree of b. And that's the basic idea. That's what we're going to use to help us with our analysis of the asymptotic behavior of these functions. Um, so maybe some details here, some stipulations. If r of x is equal to 0, that means the remainder is equal to 0. But if the remainder is 0, then your rational function is just a polynomial with some holes in it, right? So really we want a remainder. If we have a remainder, then we're going to have a quote true rational function in some sense. So yeah, it's precisely when r of x is not 0 for at least some x's that a non-polynomial rational function is produced. So we're going to specifically talk about those. We're not just going to talk about polynomials only, all right? So just like before when we talked about rational numbers, this fraction here, r of x over b of x, it contains all of the fractional information of the function. Because once you perform the division algorithm, this is like you're pulling out all of the whole components, and then you're left with a proper fraction here at the end. And this has all the fractional information of the function contained in it. All right? Okay, so I mentioned this before. We didn't use it exactly, but we're going to use it a lot in this section. So this function, this fractional part, r of x over b of x, we can call it d of x because it is quite literally a difference function. And this is the interpretation that I really want you to take away from this section and beyond. Anytime you ever have to talk about rational functions, I really want you to remember that you can write it as a quotient plus a difference function. So here I'm just rewriting it using those symbols instead, right? So here what's happened is we've taken the rational function and we've written it as q of x plus d of x. And q of x is the non-vertical polynomial asymptote of the rational function, right? So this thing could be, there you go. This thing could be a horizontal line. It could be a slanted line. It could be a parabola. That's not a great parabola. It could be a parabola. It could be a cubic function. It could be a quartic function. It could be any sort of crazy polynomial. It just depends on what this quotient is when you do the division algorithm. All right. And d of x, that is a difference function. So quite literally, d of x is going to give you the difference between the rational function itself and the non-vertical asymptote, that polynomial q of x. And here's me just showing that that is actually the case. So we can write r of x as the quotient plus this d of x, right? Well, what is d of x equal to? If you solve this, you get r of x minus q of x. So intuitively and geometrically, this is literally the difference between the rational function and its quotient. That's it, the rational function and its quotient, which is a polynomial. So in essence, a rational function is a polynomial asymptote plus some function that says how far you move away from that asymptote. So this is why we talked about graphical addition, because if you were making sense of that stuff that we talked about in chapter 2, this is the same thing. This d of x is just telling you the order relationship between the actual graph of the rational function and its polynomial asymptote. So what we can do is we can basically figure out what the asymptote is, figure out what this difference function is, and then use that to determine, hey, does the graph lie above? Does it lie below? Does it cross? Does it touch? We can do all of that by shifting our analysis to that difference function, that little fractional bit. All right. Oh yeah, a little technical term here. So technically, this quotient is called a curvilinear asymptote. So if you want to Google it and read more about it, curvilinear is the word you want to Google. I prefer to use the phrase non-vertical just to emphasize that you've got two cases. You've got vertical asymptotes, which you can determine looking at the local behavior, and then not vertical asymptotes, which you can determine by running the division algorithm. All right. But curvilinear is the technical name. Okay, so just like we saw before when we were doing a sign analysis and we had a difference function for when we were looking at a root finding problem back in chapter 2, I think it was section 2.6. If the difference is 0 for some x, then the graph of the rational function will intersect the non-vertical asymptote q of x there. Again, because the difference between r of x and q of x will be 0. That's what that's saying. If d of x is 0, then your graph, the actual rational function, is intersecting the polynomial asymptote at that point. All right? Now, remember, this is a difference function, so it gives us the order relationship. If d of x is positive, then that means that the graph of the function is above the asymptote. It's above the asymptote. And if d of x is negative, then the graph is below the asymptote. So everything we want to know is contained in this difference function. So if you ever wonder, like, hey, does my graph cross that asymptote, that polynomial asymptote, whatever it is? The answer is, well, it does if d of x equals 0, or it might bounce or cross, right? We'll tell that when we look at the difference function itself. But anytime this is 0, your graph is going to intersect that asymptote. Anytime this is positive, your graph is above it. Every time it's negative, your graph is below it. And that's pretty much it. So there's a lot of information contained in this thing. Right. Another important detail, because d of x is a rational function itself, where the degree of r is less than the degree of b, the limit, the end behavior of this fractional part is always 0. So as x goes to plus or minus infinity, that little fractional part goes to 0. And that's one of the reasons why your rational function will converge to this quotient here. So basically, as x gets big, this term goes to 0, and then you're just left with that at infinity. All right. Um, Other good news, because d of x has the same denominator as the original function written in lowest terms, it'll have the same vertical asymptotes. So it holds on to that information about the vertical asymptotes too after you've performed the division algorithm. Okay, let's do some examples here. So this one, well, let's start with this, okay? This one I want you to try on your own, at least part of it. So it says to determine all the asymptotes, vertical and not, of this function here. I want you to just find the vertical asymptotes of this function, okay? Just the vertical ones for now. All right, so think about it. You might have to refresh your memory. How do you find the vertical asymptotes? Then as always, verbalize it, speak it out loud, say something. What do you remember about finding vertical asymptotes of a rational function? Right. And now write it down. So write down what you think the vertical asymptotes are. Make sure they are actually vertical asymptotes and not holes. Just a little hint there. Okay. Now let's do it all together. So first we factor. We're going to factor the denominator. The denominator is a difference of cubes. So I hope you can kind of recognize this structure now. That's a difference of cubes. We have the difference of cubes formula. Remember, you can use SOAP to remember the signs of these terms. And here we can see that this is a potential vertical asymptote. But remember, if there's a canceling factor up here of x minus 1, then we won't have a vertical asymptote. We'll just have a hole. But that's a degree 5 polynomial. I guess I could do the rational roots theorem. I could try to factor it in all sorts of ways to see if there is a corresponding equivalent factor of x minus 1 in there somewhere. But let's use something even easier. Let's just use the remainder theorem. Remember, the remainder theorem says the remainder is going to be whatever you evaluate this thing at, right? So for a polynomial, not this thing, sorry, the numerator. If you evaluate the numerator at 1, if you get 0, then that means x minus 1 is a factor. So let's try it. I evaluate the numerator at 1, and I don't get 0, I get 3. Okay, so that means that x minus 1 is not a factor of the numerator. So this indeed will give rise to a vertical asymptote. There we go. That's our vertical asymptote. Now, what about the sorry. What about the non-vertical asymptote? So if we want to know the equation of the non-vertical asymptote, then we need to use the division algorithm. I've got it worked out here. If you want to try it on your own, you're more than welcome to. Just remember that you're going to have to include some zero terms in there, right? Because in order to get the algorithm to work the way it should, you need to include a 0x to the fourth, and then a 0x to the squared, and a 0x, just to make everything line up the way you want. But when you do that, you'll get this result. So this is the whole process right here. Remember, just kind of refresh your memory. Okay, what do I multiply x cubed by to get 2x to the fifth? 2x squared. Okay, there it is. 2x squared times x cubed is 2x to the fifth. 2x squared times negative 1 is negative 2x squared. Then you change the sign and then proceed that way, right? Now, when you do that, remember, you keep going until the degree of this result is strictly less than the degree of the divisor, which it is right here. Now, after having done that, we can rewrite g of x as this polynomial plus this difference function. This is that fractional part, right? And again, these are equal. These are equal. This is just writing it in this maybe expanded form, right? That's the basic idea. So let's look at the anatomy of this representation here. This is the quotient, q of x, this 2x squared minus 1. That is the non-vertical asymptote of g of x. And this is our difference function, d of x. So very literally, the graph of g of x looks like this polynomial asymptote, and this function is going to tell us how far to move up, down, or if it touches or crosses. That's the idea here. All right, that's the idea. Um, yeah, exactly. The relationship with the polynomial asymptote and d of x, that completely determines the graph of the rational function, all right? So I went ahead and graphed it just to really hammer this point home. This dotted red parabola, that is the parabola 2x squared minus 1. Let me zoom in on this a bit because I want to see, just want to emphasize. Oop, no, don't do that. Come back a little bit. Okay, so remember, there's a lot of information on this graph, right? But it's okay. Take a deep breath, look at it piece by piece, and remember, you know how to graph things like 2x squared minus 1. It's a parabola that's been stretched vertically by a factor of 2 and shifted down by 1 unit. That's why you'll notice the vertex is down here at negative 1. And this is just a parabola, so you know how to graph a parabola. The interesting thing now is that parabola is actually an asymptote for our rational function. Okay, we've also got this vertical asymptote right here at x equals 1. So now we know we know kind of what the graph is going to avoid unless it crosses this thing, right? So it helps to start by graphing those. Now here's the really cool part d of x, this thing right here, that completely determines the graph of the rational function. And if this thing is negative, then our graph will be below it. And if this thing is positive, then our graph will be above it. So here, you can see the graph is below the asymptote on this whole part of it, right? So this is telling us that d of x is less than 0 and vice versa. This being negative tells us this thing is below, right? And d of x, the value of d of x is literally what this is. And if you want to know how far apart they are, like the distance, you just take the absolute value of d of x and that, hey, come back, come back. There we go. There you go. And that'll give you the actual distance apart. Now on this side of the graph, okay, on this side of the graph, d of x is positive. So what's happening is when we evaluate numbers that are greater than 1, we plug numbers that are greater than 1 into here, we get a positive result. So that means our graph is above the asymptote. You might even be able to check yourself, like look at this thing, plug in some number bigger than 1, maybe like 2 or something, right? Okay, that's going to be positive, that's going to be positive, 2 cubed minus 1, that's positive, the whole thing is positive, d of x is positive, my graph is above the asymptote. That's it, right? Now do it for something that's less than 1. Okay, if I pick something smaller than 1, maybe even like 0, right? If I pick 0, that's going to be 0, positive, 0, negative, it's negative. So d of x is negative, which means we're below that polynomial asymptote. Cool stuff, huh? Super cool stuff. Okay, now that we have that idea, let me go back to this. There's a really, really important proposition, and this is one of those ones that I want you to take to heart. We're perfectly set up for it. It's this: the end behavior of a rational function is unique. Okay, the end behavior of a rational function is unique. The global asymptotic behavior is uniquely determined by that polynomial function q of x, where q of x is the quotient you get by running the division algorithm. All right. So the reason this is important is because a lot of times students will wonder, hey, can a rational function have a horizontal asymptote and a slant asymptote? The answer is a hard no, absolutely not, because that quotient that you get is unique. That quotient is a unique result, and that's a consequence of Euclid's division lemma, right? So there's only one possibility for that non-vertical asymptote. It could be horizontal, it could be slanted, it could be quadratic, it could be cubic, it could be quartic, but whatever it is, it's unique. You get one of them, all right? Moreover, when you do the division algorithm itself, you actually get the equation of the asymptote, the literal equation of the asymptote. So if you can graph this polynomial, then you can graph the polynomial asymptote. That's it. Everything perfectly coming together from what we explored earlier in the chapter. Now, as a corollary, we get this, and this is a result that you'll see in most pre-calculus textbooks. I find that students are often told to memorize it. I don't recommend memorizing it. Just remember what we just talked about that polynomial being unique, that asymptote being unique, and all of these will fall out. So here are the results. If you've got a rational function where this is the numerator, a polynomial written in standard form, this is the denominator, polynomial written in standard form, then the division algorithm will actually yield these four cases. There's four, well, it'll these four cases, I'll say. If the degree of the numerator is less than the degree of the denominator, then y equals 0 is the horizontal asymptote of that rational function, right? That's because quite literally, when you do the division algorithm, the quotient is 0. In fact, you're pretty much done before you even try to start the division algorithm. Now, if the degree of the numerator and the denominator are equal, then the horizontal asymptote will be the line y equals an over bn. It will be the ratio of these leading coefficients right here. And again, that is because of the division algorithm, because if you divide this by this and n and m are the same, then what's going to happen is those x factors are going to disappear when you divide, and you're just going to be left with those leading coefficients, the ratio of those leading coefficients. So if the degrees are equal, then the horizontal asymptote is just the ratio of those leading coefficients. All right. Case number 3, if the degree of the numerator is exactly 1 more than the degree of the denominator, you're going to have a slant asymptote. Okay, you're going to have an asymptote that's linear and not horizontal. Okay, and again, That's a consequence of the division algorithm, because if you were to divide these things and n is exactly 1 degree higher than one number higher than m, then when you do the division, you're going to end up with a linear term. You're going to end up with something times x plus blah, right? Well, if you've got something times x, that means you're going to have something that looks like this. That's a linear function, right? Okay, so that is case three. And then lastly, we have case four. If the degree of the numerator is more than one, greater than the degree of the denominator, then you have some nonlinear asymptote given by the quotient q of x. All right, so if this is, 3 and this is 1, then you've got a quadratic. If this is 4 and this is 1, you've got a cubic polynomial asymptote, and so on and so on. And again, all of these cases are simple consequences of the division algorithm. That's it. So if you can do the division algorithm, all of these pop out. Boom. Okay. Now we need to talk about what's called asymptotic equivalence. So oftentimes we're not concerned so much with the precise non-vertical asymptote of a rational function, just its end behavior. We just want to know what's going on at the end, right? And since the asymptote is a polynomial, the end behavior of the rational function is the same as the end behavior of that quotient, that polynomial quotient that you get, which we studied in great detail when we talked about polynomials. So summarizing, we get the following proposition, which gives us an easy way to tell roughly what's going on at the end. So let's say you've got a rational function, a of x over b of x. Numerator is a polynomial in standard form. Denominator is a polynomial in standard form. Then the limit as x goes to plus or minus infinity of r of x is equal to the limit as x goes to plus or minus infinity of the ratio of the leading terms. That's it. And we're going to see exactly why in just a minute here. But what this is saying is the end behavior of the rational function is the same, right? Equal means the same as the end behavior of the ratio of these terms. So you basically look at this, you look at this, you divide them, and whatever you get, that's the end behavior of r of x. It's not going to give you the exact quotient. It won't give you the exact polynomial asymptote, but you can read off the end behavior like that. Literally just look at the end behavior and you got it, okay? So this proposition is actually a statement about what's called asymptotic equivalence. And this stuff becomes really important later on in math and science because, I mean, computer scientists study this stuff all the time. We want to know what happens when processes are run indefinitely, and we want to know where those processes lead if you run them a million times, a billion times, a trillion times. Like, what is the end behavior? And a lot of times, what is easier to study is the ratio of a function that we're interested in and a function that we know about. Yeah. And then what we do is we look at what happens to that ratio at the end. We look at the end behavior of that ratio. And that leads us to what's called asymptotic equivalence. So we say two functions f and g are asymptotically equivalent if and only if the limit of their ratios is equal to 1. Okay, the limit of the ratio is equal to 1. Um, it could be either direction. It can be to positive infinity, to negative infinity. You can also modify this to talk about local behavior. But the basic idea is, hey, if the end behavior of this thing is the same as the end behavior of this thing, then this limit is going to give you 1, right? Kind of like they're doing the same thing at infinity. So that's what we mean when we say asymptotically equivalent. The cool thing is we have a cute little notation for this. We write f of x tilde g of x. I can zoom in a bit there. There we go. So when you see this little single squiggly line, what we mean is f of x is asymptotically equivalent to g of x, which means the end behavior is the same. That's really what that means, okay? Okay, now we have all the tools we need. Now we're going to finally put all of this stuff together and do some cool stuff. We know everything we need to know to determine the graph of a rational function given its formula and make a sketch of it by hand, all right? The following is a 7-step procedure that can help organize the process. You don't need to follow these steps exactly the way they're written. You can do them in any kind of order you want. This is just to kind of help organize your thoughts. And in my experience, it helps to create the graph as you go along, to maybe off to the side, start sketching like the vertical asymptotes, maybe plot where the zeros should be, and then continue from there. All right. So here is the 7-step process. One, examine the ratio of the leading terms to see the general end behavior. So basically find out what your function is asymptotically equivalent to. That's it. Once you've got a rough idea what the end should look like, factor the numerator and the denominator completely. Find the domain by examining the zeros of the denominator. Once you have the domain determined, note where any holes occur, and then cancel whatever you can, putting the graph or the function in lowest terms, right? So you basically are like, okay, I know what it's got to look like at the ends. Let me factor everything now. Factor everything. What's the domain? Can I cancel anything? That's step 2. Now, once you've done that, find the vertical asymptotes. Look at the zeros of the denominator for the function in lowest terms, find the vertical asymptotes, and then sketch them using a dashed line. We usually use dashed lines for asymptotes, okay? Use multiplicity and the global end behavior to determine the behavior of the graph of R on each side of the vertical asymptotes. So if you remember, there was an example I did in the previous section where remember the behavior around the vertical asymptotes is either going to look like plus or minus 1 over x, or it's going to look like plus or minus x squared. Sorry, 1 over x squared. Basically give yourself an idea of that. And now that we know what's happening at the end, we can really see where the graph is going to lie with respect to those vertical asymptotes. Okay, now find and plot the x and y intercepts of the graph. Again, you can do these in different orders. You might even want to do this step before step 3. That's totally fine. But find all the x-intercepts. You do that by looking at the zeros of the numerator. Find the y-intercept by plugging in x equals 0. Use multiplicity and end behavior to determine the behavior of the graph at each intercept. Remember, if the multiplicity is even, then the graph will look like x squared or negative x squared at that point. If the multiplicity is odd, then it either is going to cross like a straight line or it's going to cross like a cubic function, right? All that stuff coming together now. Okay, now find and sketch the non-vertical polynomial asymptote by doing the division algorithm. So this is where you basically take a step back, go back to the original representation of R of x, and divide. Do the division algorithm, rewrite R of x as its quotient plus that difference function, and then we're going to do a sign analysis on that difference function. So create a sign diagram for d of x, mark its zeros, mark its vertical asymptotes, test points to determine if the graph intersects, lies above, or lies below the non-vertical asymptote. And with all that information, you can sketch the graph. All right. Let me kind of summarize all that a little quickly because I know that's a lot. So let's be a little more quick about it. First, look at the end behavior. What's it going to behave like, roughly speaking, at the ends? Factor everything, find the domain, find any holes, find the vertical asymptotes, find the zeros, find the y-intercept, then do the division algorithm and figure out if it lies above or below that non-vertical asymptote, and that's it. Okay, that's basically the idea. So let's practice this. This is going to be fun. Maybe, hmm, hmm. Okay, I'll do this one, and then I want you to try the next one on your own, just so you can kind of see how it goes. We're going to analyze the graph of this rational function here using that 7-step process. So I remember this. Step number 1 is get the rough end behavior. The rough end behavior is going to be the ratio of these leading terms. So when I divide x by x squared, I get 1 over x. So that means R of x is asymptotically equivalent to 1 over x. So the end behavior of R of x is going to be the same as the end behavior of 1 over x. That graph that you remember really well, right? So at the ends, that's what it's going to look like, okay? That's what it's going to look like. In particular, we know that we're going to have a horizontal asymptote of y equals 0 in this case. Okay, next, factor everything. Factor everything. Numerator, denominator. Denominator is a difference of squares. It factors as x minus 2, x plus 2. There are no common factors in the numerator and denominator. The domain is everything except plus or minus 2. And there are no holes. No holes. Step 3, these have to give rise to vertical asymptotes because there's no equivalent canceling factor in the numerator. So let's just start sketching. Let's start by sketching those vertical asymptotes. Get a template going, right? So we're going to do those right there. Okay, now the multiplicity of these two things is 1, and that's odd, so we know now that around these asymptotes, the graph is going to look like 1 over x plus or minus, right? And in fact, because we know the end behavior is also going to be like 1 over x, we know that this is going to roughly look like this and this and this. Oops, let me make that a little more. There we go. At this point, I just have a rough picture of it in my head. Why? Because 1 over x goes like that. So my end behavior is going to look like that too. The multiplicity of this asymptote is 1. So it's got to look like that and like that. Oops, sorry. What am I doing? That and that. Okay. And then this one's the same way, right? But remember, 1 over x goes like that. So this is going to have to be like that, which means this is going to have to come down somehow. Everything is kind of falling into place. All the puzzle pieces start to fit together. All right. Um, Let's find the x and y intercepts. The x-intercepts are the zeros of the numerator, in this case 1. So you could actually plot that. You could go and plot the x-intercept on your graph. It's 1. The y-intercept occurs when x equals 0. So we plug in x equals 0, simplify, and we get 1/4. So now we know the y-intercept is 1/4. It's going to be about here. We had our x-intercept there. Now it's really starting to agree with this, right? Okay. Um, that's it. Now, the division algorithm part, okay? The way that you do this is up to you. You can use whatever algorithm you remember. You just need to rewrite this function, this original function, in terms of a quotient and a difference function. Now, in this case, notice that the degree of the numerator is already less than the degree of the denominator. So the division is already done. It's already done. If we tried to run the division algorithm, we would get 0 as the quotient. So r of x is literally 0 plus d of x, which means r of x is equal to d of x. So d of x is just r of x itself. This is what happens when the degree is already, the degree of the numerator is already less than the denominator. Maybe more intuitively, always, go back to intuition. Think of a rational number. Here, this rational number is 0 plus something. That's it. 0 plus 1/2, 3/4, or something like that. So the integer part is 0. That's what's happening, right? The numerator is less than the denominator, so it's already written as a proper fraction, which means the quotient here is going to be 0. The quotient is just going to be 0. So that means our difference function is just the function itself. Now we do the sign analysis that we already saw in chapter 2. We saw it again when we were looking at polynomials. Do the same thing, turn all of your attention to d of x. Here we go. D of x has two asymptotes, -2, +2, and it's got a 0 at 1. We're going to mark that there. So we basically have two asymptotes, two asymptotes and a 0. Then we're going to test points all around those. Test this point, we get a negative. Test this point, we get a positive. Test this point, we get a negative. Test this point, we get a positive. So this is telling us where our graph is going to lie with respect to the polynomial asymptote. In this case, d of x is just equal to the x-axis, the line y equals 0. Now we have all the information, we can sketch it, and lo and behold, it looks what I had imagined. Looks like what I had imagined, right? End behavior is like 1 over x. Here's that y-intercept. Here's that x-intercept. Notice that around this vertical asymptote, it behaves like this. Crosses the y-axis right there, crosses the x-axis right there, keeps going down, and the behavior here has to look like 1 over x. And there we go. Here, this is our polynomial asymptote. In this case, it's a horizontal line. It's the line y equals 0. Pretty sweet stuff, huh? It's awesome how it all comes together. Okay, let's do another example. Here's this one, and I want you to try this one on your own, and then we'll do it together, all right? So ponder it for a minute, just kind of look at it, look at the function itself, think about it for a minute. Okay. Now verbalize something, give your brain some feedback to tell you what you're thinking. Talk it out loud, say it out loud, talk it out with someone. Better yet, if you're with somebody watching this right now, talk to them, even better. If you're in like the math lab, just turn to somebody next to you and be like, hey, what do you think of this function? Okay. And now try to work it out. Remember, you can follow that 7-step process. You don't have to do it in the exact order. You can do it in different orders. Just remember end behavior, factor everything, find intercepts, do the division algorithm, and sketch. Okay, here we go. All right, now let's do it together. First thing I notice is the ratio of the leading terms is x. So this graph is going to behave roughly like y equals x at the endpoints, or I'm sorry, at infinity. So it's going to look like roughly like a slant asymptote y equals x. Okay. In this case, it's already factored, so there's no canceling factors or anything like that. The domain is everything except x equals 0. We've got an x-intercept at 1, an x-intercept at -1. Um, there is no y-intercept. There's no y-intercept because x can't be 0, so it does not cross the y-axis. That also means the vertical asymptote is going to be x equals 0, and there's only one of them. Geez, that was like the first 4 steps, I think, right? So then what's left is we need to do the division algorithm and write it as a quotient plus a difference function. In this case, yep, this is everything I just said. Everything I just said out loud. In this case, we could actually save ourselves a bit of trouble. This is only one term down here. So we could actually split this up into 2 fractions and just simplify, reduce the fractions. So when we do that, we get this. There we go. Yeah. X minus 1 over x. So x is our quotient, and -1 over x is the difference function. Okay. Again, notice that we're taking that sign with us, that negative sign, because we're writing it as q of x plus d of x. Excuse me, q of x plus some difference function. Now we need to do a sign analysis on our difference function. Here we go. -1 over x. It's got no zeros. It's got an asymptote at x equals 0, so we plot it, and then we test points. If I plug in -1, I get a positive number. If I plug in +1, I get a negative number. So now we know everything we need to know. Remember, this is representing the asymptote, the polynomial asymptote, in this case, that slanted line. So our graph is going to be above the slanted line over here, and it's going to be below the slanted line over here. Now we've pretty much got everything we need. Boom. That's what it looks like. Um, Here's our 2 x-intercepts. There was one vertical asymptote right there. Here's our slant asymptote. Remember, there's no y-intercept because x can't be 0, so we're witnessing that here as well. Our sign analysis said our graph has to be above this line over here, and it said it's got to be below this line over here, and that's it. It's done. Pretty cool, huh? Cool stuff. All right, let's do one more just to hammer things home. Okay, here, I want you to try this one a little bit on your own as well. So again, think about it. Think about it for a minute, stare at it. Okay, now verbalize something, say it out loud, talk to your dog, talk to your cat, be like, what do you think this is going to look like? All right, and now try to work it out, and we'll do it together in a moment. All right, here we go. All right, so Oh yeah, usual. So first thing, look at the ratio of these two leading terms. X to the fourth over x squared is x squared. So our function is asymptotically equivalent to x squared, means at the ends, it's going to look like x squared. Remember, this is not, oh, here, let's do that. Remember, this is not the exact asymptote. It's just the end behavior. That's why we're using that squiggly line. It's going to behave roughly like this at the end. It's going to be like that at the end, right? Let's see, we need to factor everything. So factor everything over R. The numerator factors like this. Couple of steps, right? So this is a difference of squares. It may not look like it on the surface, but it is. It's x squared squared minus 1 squared, and that's why we factor it like this. But then when you do that, this result is also a difference of squares. So you can factor it even further. Denominator is also a difference of squares. It factors as x squared minus root 2. So, I'm sorry, x squared, x minus root 2 times x plus root 2. There we go. Now that it's fully factored, we can see that there are no common factors in the numerator and denominator, so it's already in lowest terms. That means these are going to be vertical asymptotes. The domain is everything except plus or minus root 2. Our zeros, our x-intercepts are going to be 1, -1. This one does not yield any x-intercepts because we're only talking about real numbers. And geez, what else? We just got a lot. End behavior, x-intercepts, asymptotes. We need the y-intercept. So the y-intercept, oh, I didn't actually put it on here. Yeah, I didn't calculate it. The y-intercept, oh wait, no, didn't I? Oh yeah, it's right here, right here. Just missed it. Y-intercept, you plug in x equals 0. You can use whichever form you want. Remember, these two forms are equivalent. They have the same value. So I plug in 0, I plug in 0, I get -1 over -2. That's 1/2. That's our y-intercept. Now we need to do the division algorithm. There's no shortcut here. We can see that the degree of the numerator is greater than the denominator, so we are going to get a result when we perform the division. So here we go. Uh, Same thing. What do I multiply x squared by to get x to the fourth? X squared. X squared times x squared is x to the fourth. X squared times -2 is -2x squared. Change the signs. Keep going. And then this is the quotient that we get, x squared plus 2. All right, so this rational function looks like x squared plus 2, but then pushed away up or down by this amount right here. One thing I really do want to point out here explicitly is that in the beginning, we found that the end behavior was going to be like x squared. But notice that that's not the exact asymptote itself. The asymptote itself is x squared plus 2. So note that when we have that little squiggly line, it really is a squiggly line. It's not an equal, right? It's not an equal sign. So that's the asymptote. That's our difference function. We're going to focus all of our attention on d of x now. All right, here we go. D of x, it's got no zeros. The numerator will never be 0, so that means that our rational function is not going to cross the asymptote or even intersect it. It's not going to bounce off it, not going to cross it. D of x has two vertical asymptotes that are equal to the ones of the original function, so we can plot those. Then we test values. We test values in d of x to see what we get. So I plug in -2, I get a positive. I plug in 0, I get a negative, right? If this is 0, I get -3/2. If I plug in 2, I get a positive number, right? Okay, so our graph is going to be above that parabola here, below that parabola there, and above that parabola there. These both have multiplicity 1, so the graph should look like 1 over x around those asymptotes, or -1 over x. Put it all together, and boom, sad face, sad face. Anyway, sad face, but still pretty fun. So here's our vertical asymptotes right there, -√2, +√2. Here is x squared plus 2. There it is. Again, the multiplicity of these asymptotes, I'm sorry, remember the end behavior is going to be like x squared. That's what we determined. So it should go up like that and up like that. Um, the graph was above the polynomial asymptote over here. That's why we're getting this. The multiplicity of, oops, this one of x equals negative root 2 is 1, so it should behave like 1 over x there. It's got to behave like 1 over x or negative 1 over x there. It's going to swoop back down. Look at our intercepts, right? This is 1/2. That's our y-intercept. Negative 1 and 1. Those are our x-intercepts. So it goes like that. There we go. I always debate making this one a smiley face instead, and then but then you would just have you'd have something like this. So it just looks like a weird long face kind of thing. Anyway, that's it. So that is how we analyze those things. Now, let's flip things around. Let's try to go backward. Let's say we start with the graph of a rational function. Can we come up with a formula, at least a somewhat rough formula of what this is going to look like? This is one I do want you to try on your own first. Remember, we're going in reverse, right? So I want you to come up with the formula given the graph. So let me zoom in a little bit for you. There we go. And again, there's many different answers, so just go with one that you think would be right, all right? So first you got to think about it. Oh, sorry, that's not it. Hold on, hold on. There you go. Think about it, right? Start verbalizing some things. Maybe say out loud one thing you notice about the graph. Okay, and now try to work it out. Try to write a formula for that. It's going to be a rational function. Couple of hints I will give you. Look for intercepts, look for asymptotes, look at the behavior of those intercepts and asymptotes, and consider how that affects the multiplicity. All right? We'll do it together in a moment. Okay, here we go. Okay, so if I had to verbalize some things, first thing I am noticing is, well, we've got a horizontal asymptote right here at 1, 2, 3. It's a horizontal asymptote. So that means the ratio of the leading terms is going to be 3. And let's see, we've got two vertical asymptotes, right? This one is at -4. This one is at 3. This one looks like 1 over x, so the multiplicity has to be odd. This one looks like 1 over x squared, so the multiplicity has to be even. What else? Oh, we've got an x-intercept right here at -2. We've got another x-intercept here at 5. And frankly, just with that information, that's enough to get a rough formula for it. Here we go. Here's the formula I came up with. Yours might be a little bit different. Maybe another note I'll say is you don't need to write it in standard form. You can leave it in factored form. That's okay. But here's the 3 corresponding to that horizontal asymptote. Here's x equals -2 with multiplicity 2 because it's bouncing, right? It's bouncing off of that. Here's x minus 5 multiplicity 1 because it's crossing, right? Looks like y equals x. Denominator, so we have an asymptote at -4, multiplicity 1. And then x minus 3 looks like 1 over x squared, so multiplicity 2. And that should be it. That should be it. Yep, that's it. There we go. Pretty cool, huh? So again, that those big ideas and that intuition can really, really guide you when you're trying to do these problems. You don't need to rely on algorithms for everything. You can kind of look at the pieces and be like, wait, it should look roughly like that. The moment you want to get more specific, if you want to have a perfectly drawn graph, that kind of thing, then you need to go to a computational resource most of the time. Desmos, Mathematica, your calculator, like they can graph these things easily, right? A lot of times we just need a rough sketch so that we know roughly what's going on. Okay, actually, speaking of technology, let's talk about some helpful technology. So, naturally, Mathematica can perform the division algorithm. It can produce the formula for the polynomial asymptote of a rational function. We've already seen a bunch of commands that are going to help, like factor, numerator, denominator. Those can all be used to help with our analysis, just like we saw last time. There's another really cool command that we're going to use right now called polynomial quotient remainder. And that quite literally produces the quotient and the remainder that you get when you divide two polynomials. It produces the polynomial quotient and the remainder. You just put in the numerator, you put in the denominator, you tell it what the variable is, run it, and it will spit out a list that gives you the quotient and the remainder. Pretty sweet. Let's try it. We're going to try it on this one. Yeah, okay, so hopefully when you see something like this, you feel a little twinge like, oh my gosh, you don't want to have to do that by hand. It's going to be pretty rough. I mean, this is degree 6. This is degree 3. If you wanted to actually graph it, or if you wanted to find the quotient, like the polynomial quotient, it's going to be a long process. Uh, this is ripe for computers to help us with, right? Oh, one thing I can tell right off the bat, look at the ratio of the leading terms. 6x over x cubed, maybe I'll write this out. So 6x, sorry, so the sixth over x cubed, that's equal to 6x cubed. So that means whatever this thing is, it's asymptotically equivalent to 6x cubed. That's what it's going to look like roughly at the end, right? It's going to look kind of like that, speaking of end behaviors, okay? Let's go over to Mathematica and take a look. I want to know what I would get if I had to do the division algorithm. There it is. Okay, here we go. Yeah, okay. So what I did was this. I went ahead and I instantiated the function r of x here so that it was easier to refer to. I didn't have to keep entering it. So, and I actually remembered to call it this time so you can actually see it. There we go. So I hit shift return, and this is just me verifying that this is what it should be. Remember, Mathematica writes things in reverse standard form because it likes to list it in terms of increasing degree, 0, 1, 2, 3, 4, 5, and so on. Okay, remember numerator just picks out the numerator, denominator just picks out the denominator. Let's verify. I went ahead and instantiated these as their own function for ease, for efficiency. Okay, and then there's this one. Yep, that's the numerator. Yep, that's the denominator. And now here's the new function that we're learning, polynomial quotient remainder. And again, you enter the numerator, comma, enter the denominator, comma, and then tell Mathematica what the variable is, what the input variable is. Let's run it. There we go. And it gives you the quotient and the remainder. Oof, those numbers, man. Again, this is why we like technology. So what this is telling me is if you were to run the polynomial division algorithm by hand, this would be the quotient you get, and this would be the remainder that you get in the end. Pretty rough, all right? But that's it. So now that we know the quotient, we know the remainder, we can write r of x in that form, right? So let me go back to the slides. We can write r of x in that form. Here it is. Okay. Zoom in a tiny bit at the bottom. This is just me putting in that code. This is the output that we just saw, and that's it. Here's the quotient. That's the polynomial asymptote. This is the remainder that it spit out. And then to get the fractional part, oops, there we go. And to get the fractional part, we just do the remainder divided by the divisor, and that's it. Again, notice the degree of the numerator is less than the degree of the denominator, so this is a proper fraction, right? A proper fraction. And if you were to take the end behavior of this, it would be 0, and that's it. So again, that's why we like Mathematica, we like technology. Okay, on that note, let's play, all right? I hope you liked this one. This is a great way to round out the chapter. I think it's a great way to end chapter 3. I hope you really enjoyed learning about polynomials and rational functions, and I hope you enjoyed this analysis. I just think it's really fun at the end. It's just fun to see how all those pieces come together. Even things that we were talking about in chapter 1 and chapter 2 and earlier in chapter 3, they all come together to make this analysis really, really straightforward, maybe complicated, or I should say maybe difficult, but straightforward, right? All right. Thank you all again for watching and listening, and I will see you in chapter 4 next. Chapter 4, we're going to talk about exponentials and logs, all right? Okay, take care, everyone. I will see you next time.